Finding sides with trigonometry. Previously we learned that every single right-angled triangle with the same angles has matching ratio of sides. So it wouldn't matter how many times I drew exactly similar triangles. If they were indeed exactly similar and their angles were the same and they're all right-angled triangles, then when I did opposite over adjacent, for example, we discovered that if they're similar triangles, I'll always get the same ratio. Now that means if I know the angle, my calculator can look up the ratio for me, because it's stored for every single possible angle. The ratio of opposite over adjacent is stored in the calculator, and opposite over hypotenuse and adjacent over hypotenuse, all those individual ratios for every possible angle from 0 up to 89.9, they're all stored in the calculator. So we discovered that firstly, similar triangles have the same ratio of sides and they're matched up with the angle, so if we know the angle, we can find the ratio. This is how we use this to find unknown sides in trigonometry. My first example is trying to find the height of a tree. Once you get more than a meter or so high, a couple of meters, it's very hard to measure the height of a tree. Climbing a tree is tricky. You can't get the measuring tape up there. There's an instrument called a clinometer. I'll write that down there. We don't need to know that. But it measures an angle when you look up or down at something. So a typical way of measuring or calculating the height of a tree is to stand or lie down on the ground is even better, a certain distance away from it, and measure that distance. So let's say our person who needs to measure the tree has carefully measured out 20 meters away from the tree, and they lie down on the flat ground so that we assume the tree is vertical and the ground is flat and we've got a right-angled triangle. And they use a clinometer to look up as accurately as they can at the very top of the tree. And you'll see that makes a right-angled triangle. With their clinometer, they measure that angle between the ground and where they're looking up. So they very carefully measure that, and we'll give them a 25-degree angle. Now we'll go out at some stage and do this ourselves and get some practice at it. But really, what we need to be able to do is do this on paper. Now, what they want to know is the height of the tree. And you'll see now that we have a right-angled triangle, 25 degrees. We want to know the opposite, and we have, a 20-meter adjacent. Sorry about my tiny drawing. We know that the ratios can be found out if we've got a 25-degree angle. And I've got opposite and adjacent. So I'll be finding out the tan ratio. And it will be tan of 25 degrees. And if we type that into our calculator, which I'm sorry I don't have displayed for you today, but we just type in tan 25, and that equals 0.466. But of course the other thing we know is that tan means opposite over adjacent. So really, the opposite over the adjacent equals tan 25, and that equals 0.466. And we know the adjacent, it's 20 meters. So the opposite was x, the adjacent was 20, and I know that's got to be 0.466. And I know we're not used to equations with decimals in them, but that's just an equation. If I'd said x divided by 20 equals 3, then you could solve that easily. You'd say I need to get rid of the divided by 20, so I'll times by 20 on both sides. X is 3 times 20, x is 60. Now, but I didn't tell you x divided by 20 was 3. I told you x divided by 20 was 0.466. But we solve it the same way. I need to get rid of the divide by 20. So x will be 0.466 times 20. Again, grab your calculator and work through that with me. 0.466 times 20 says x equals 9.32. That's 9.32 meters for the height of the tree. Now that's showing you why it works. It works because if we know the angle and which ratio we've got, we can find out what the ratio should be and use that to find the unknown side. So it's very like similar triangles where we find the scale ratio and multiply to find the unknown side. But actually we don't have to do the working quite like this. So very quickly, here's an example from the textbook of how we'd show the working. First step, label the sides. Hypotenuse is 5, and opposite to 20 is x, so that's the opposite. There's nothing on the adjacent side, so we can't use an adjacent side ratio. So we choose the only ratio that's got the opposite and the hypotenuse, and that's sine. So our second step is always choose the ratio. We write sine theta equals opposite over hypotenuse. Every time we must write the ratio exactly like that, including theta. Our third step is substitute the values. Sine of the angle. Now the angle was 20 degrees. We must put that in. Equals. The opposite we don't know. We put x. The hypotenuse was 5. Before, when we worked this out with the tree, we worked out what sine of 20, or we worked out what tan of 25 degrees was, and we used that number. We could do that with sine of 20 degrees and work out what it is and then rearrange, but it's actually quicker to just say, I want x on its own. I've got x divided by 5. Let's multiply the other side by 5. So 5 times sine of 20 degrees equals x. So we just type into our calculator 5 times sine 20. We don't need to do the degrees. And we discover that x is 1.7 centimeters. That is the exact working we need to show. Okay, you don't need to draw the arrow if you don't want to. Our fourth step is to solve once we've got the equation, and your working should always look exactly like that. Label the sides, choose the ratio that uses the sides that we've got, substitute your values in, and rearrange to get x. If you didn't understand why it works with the tree example, it's okay. You can just remember how to solve it. But the lovely thing about trigonometry is it's so much easier when you understand why it works.